1 minute ago, off the coast of California, the seafloor began to rise. Yet this isn't a volcanic eruption or an earthquake, and even seasoned scientists can't explain it at first glance. Instead, entire neighborhoods are being nudged toward the Pacific as millions of tons of ancient land slide downward, forcing new ground to bulge upward from the ocean, reshaping the coastline before our eyes. With roads collapsing and homes declared uninhabitable, what invisible force has triggered this paradox? How can falling land make new land rise from the sea? The answer begins deep beneath Rancho Palos Verdes. Long before any road was built or home perched on the bluffs, the southern edge of the Palos Verdes Peninsula was already restless. The ground here is a patchwork of ancient landslides, shaped by thousands of years of slow, relentless movement. Beneath the surface, the earth is layered like a tilted deck of cards, sedimentary beds that all lean seaward, pointing toward the Pacific. This tilt is no accident. Over millions of years, sediments settled out of an ancient ocean, then hardened into shale and tuff, their layers quietly sloping downward. The real trouble, though, lies in the slippery boundary hidden deep below, a band of bentonite clay born from volcanic ash that runs like a ribbon through the Altamira shale. When dry, this clay is just another layer in the stack. But when saturated by rain or groundwater, it transforms into a near frictionless slide plane. The friction angle in these clays can drop as low as 6 degrees, so low that even a gentle push from gravity is enough to set entire hillsides in motion. Geologists have drilled boreholes and pulled up core samples showing how the bentonite swells when wet, losing what little strength it had. Water pools above the clay, unable to drain, building up pressure until the overlying rock starts to creep. Over centuries, this process has created a landscape defined by movement. The largest of these ancient slides sprawls across more than 700 acres, reaching from the uplands down to the sea. Its boundaries are mapped by subtle scarps, offset gullies, and the occasional pressure ridge where the mass has buckled upward. This is a classic dip-slope landslide. The ground above rides down the tilted bedding, lubricated by clay, with the entire mass moving as a slow, unified block. This deep-seated instability is the invisible engine behind today's drama, the same geologic setup that, under the right conditions, can force the seafloor to rise, even as the land above slips toward the ocean. The story of Rancho Palos Verdes begins not with a sudden disaster, but with a landscape quietly primed for motion, waiting for the next push. In 1956, the quiet geology of the Palos Verdes Peninsula was jolted awake by a single human decision. Plans to extend Crenshaw Boulevard meant grading a new road across the upper slopes, slicing deep into the hillside. Engineers cut through layers of ancient shale and tuff, exposing the bentonite clay beneath. Heavy machinery carved channels for storm drains and shifted the natural flow of groundwater. What seemed like routine construction set off a chain reaction. As water seeped into the newly disturbed ground, it pooled above the clay, saturating the slip plane and lowering its friction even further. Within months, the hillside began to move, not just a trickle, but a slow, relentless surge. Surveyors measured the first signs: fences out of alignment, fresh cracks in the pavement, and subtle tilting of telephone poles. By the end of that year, the entire slope, nearly a mile wide, was in motion. The Portuguese Bend landslide, once a dormant feature mapped by early geologists, had reactivated on a scale no one had witnessed in modern times. The ground shifted by as much as 8 feet per year in some places. Neighborhoods built on what was thought to be stable land found themselves creeping toward the sea. Roads buckled and split, forcing constant repairs. The city's engineers realized the magnitude of the problem only after it was too late to reverse. Decades of slow movement followed, with each rainy season accelerating the slide. The cause was clear in the records. A combination of deep-seated geology and a single episode of construction that disrupted the delicate balance of water and clay. What began as a plan to connect communities ended up unleashing the largest active landslide in Southern California. The consequences of that decision are still unfolding as the ground continues to shift beneath homes, roads, and the coastline itself. On a September morning in 2023, residents awoke to find Palos Verdes Drive South transformed overnight. Fresh cracks zigzagged across the pavement, curbs twisted out of line, and a jagged offset split the road surface where it had once been flat. Surveyors documented a new gap just over a foot wide where the ground had lurched in opposite directions. Emergency crews closed off the stretch within hours. Drone footage circulated online, showing the break from above. A sharp, unnatural step in the asphalt, power lines sagging overhead, and orange cones marking the boundary between passable and lost ground. The city's engineers measured the displacement and confirmed what drivers already knew. The land here wasn't just creeping, it was shifting in sudden, unpredictable bursts. Residents described the shock of headlights bouncing as cars crossed the brake, the sound of concrete splitting underfoot, and the uneasy realization that nothing was stable, not even the main road connecting their homes to the rest of the peninsula. 20 homes in the immediate area were red-tagged following the event, their owners ordered to evacuate. On some blocks, entire families packed up in a single afternoon, leaving behind furniture, toys, and half-finished gardens. The city's official notices, stapled to front doors, spelled out the risk. Active ground movement had rendered these structures unsafe for habitation. For many, the warning came after weeks of mounting anxiety. Doors jamming, floors sloping, fences pulling apart at odd angles. One longtime resident speaking in a local news interview captured the daily uncertainty. "We had to move the fence 3 times. It's like the ground itself tries to walk away." In the weeks that followed, city crews patched the road yet again, only to watch new cracks form just feet from the old ones. The pace of change left little time for adjustment. What had once been the slow-motion drama of geological time now played out in the span of a single night, forcing an entire community to adapt, improvise, and confront the reality that the ground beneath them was anything but solid. Each morning brings a new reminder that life in Rancho Palos Verdes is anything but predictable. In backyards and along property lines, fences once set straight now zigzag across the landscape, their posts leaning at impossible angles. Some residents have grown used to resetting their boundaries every few months, moving a fence 3 times in a single year, or watching a gate drift so far off course it no longer closes. Time-lapse videos, shared in online forums, capture the surreal pace. Patio tiles separating by inches, garden sheds slowly marching down slope, and backyard trees left stranded on islands of earth as the ground pulls away beneath them. The changes aren't just cosmetic. Utility crews work around the clock, patching ruptured water mains and splicing power lines that have been stretched to the breaking point. On some blocks, outages are a weekly occurrence. Families keep flashlights and bottled water close at hand, never sure when the next disruption will hit. Gas service is a constant worry. Underground pipes can't flex with the shifting soil, so leaks are an ever-present risk. Even the internet, once taken for granted, becomes unreliable as fiber optic cables buckle and snap beneath the moving ground. For many, the psychological toll is harder to measure than the physical damage. Neighborhood message boards fill with anxious updates, photos of fresh cracks in driveways, questions about insurance, and stories of sleepless nights spent listening for the telltale sound of foundation beams creaking in the dark. Some residents joke about living on a moving sidewalk, but the humor wears thin as the months drag on. The uncertainty seeps into daily routines. Parents reroute school drop-offs around closed roads, gardeners abandon flower beds that have slumped out of reach, and homeowners weigh whether to invest in repairs or simply wait for the next round of movement to undo their efforts. Despite the constant upheaval, a sense of community persists. Neighbors share tips for patching walls, lend each other tools, and document the changes together, turning private frustration into a kind of collective resilience. But beneath the surface, the strain is unmistakable. Every new crack, every shifted fence, is a reminder that the ground here is always in motion, and that adapting to this reality has become a way of life. Beneath the chaos of shifting roads and tilting homes lies a layer that geologists have studied for decades, a seam of bentonite clay, born from ancient volcanic ash that acts as nature's own lubricant. In the laboratory, samples of this clay reveal just how little resistance it offers. When dry, bentonite behaves like a soft stone, but once water seeps in, the particles swell and the friction drops to almost nothing. Direct shear tests show friction angles plunging as low as 6 degrees, far below what most soils or rocks would allow. For context, dry sand typically resists sliding at angles above 30 degrees. Here, the saturated clay allows movement on slopes barely steeper than a wheelchair ramp. This ultra-low friction is not just a curiosity. It's the key to the entire landslide's motion. The bentonite forms an almost continuous, slippery plain beneath the overlying rock. When rain or irrigation water percolates down and pools above this layer, the pressure builds. The overlying mass, heavy with homes, trees, and roads, finds itself perched on a surface so slick that even gentle gravity is enough to set it creeping. Groundwater doesn't just lubricate the clay, it also creates a perched water table, trapping moisture right at the weakest point. The result is a system where the addition of just a few inches of rain can tip the balance from stability to movement. Engineers and geologists have measured these properties in both field and lab settings. Core samples pulled from deep boreholes confirm the swelling and softening of the bentonite after storms. In the lab, direct shear boxes measure the precise angle at which the clay will fail. Numbers from these tests, friction angles between 6 and 12 degrees, cohesion values as low as 5 kilopascals, match what's observed in the field. Large blocks of hillside gliding down slope, almost as if on ice. The movement is so efficient that it doesn't grind the rock into debris. Instead, entire slabs slip as a single unit, leaving behind polished surfaces and slick, blue-gray smears of clay. This mechanical simplicity explains why the landslide's motion is so hard to stop. As long as water can reach the bentonite, the ground above will remain prone to sliding. Dewatering wells and surface drains can slow the process, but they can't change the fundamental physics. The numbers from the lab translate directly to the landscape outside, where a 6-degree friction angle means even a gentle slope can become a conveyor belt for the earth above. The Portuguese Bend landslide is not a chaotic jumble, but a slow-motion demonstration of what happens when geology and water conspire to erase friction from the equation. Gravity pulls the landslide mass downslope, but the story doesn't end there. At the seaward edge, the toe, something unexpected happens. As millions of tons of earth slide forward on the slick, bentonite-rich ramp, the land encounters a hidden rise in the failure surface beneath. The sliding mass cannot simply plow straight through. Instead, it is forced upward, bending the ground at the toe and lifting new land above the waves. This is not a sudden jolt, but a steady, mechanical process, almost like a slow-motion lever. Geologists describe it with a simple formula: U equals h times the tangent of alpha. U is the vertical uplift, h is the horizontal distance the slide moves, and alpha is the angle of the buried ramp. For a 5-meter downslope movement over a 10-degree ramp, the toe can rise nearly a meter. If the ramp steepens to 20 degrees, the uplift more than triples. These numbers aren't just theoretical. Pressure ridges and bulges at the coast match the calculations, and offshore, sonar surveys reveal new sediment bulking where the slide reaches underwater ramps. This uplift is visible proof of the hidden force at work, a direct conversion of horizontal movement into vertical rise. Yet the process is locked in a cycle. As soon as new land appears above sea level, the Pacific Ocean attacks, eroding the toe with every wave. The coastline advances, then retreats, in an endless loop. Each storm strips away the uplifted edge, clearing the way for the next surge of sliding earth to push the toe upward again. The math plays out in real time. For every meter of fresh uplift, the ocean claws much of it away within months. The result is a coastline in constant flux, shaped by the competing forces of gravity and surf. Physical models in the lab confirm what's happening beneath Rancho Palos Verdes. Clay-rich sandboxes, tilted and loaded, show the same pattern. Push the mass forward, and the toe jumps up as it rides over a ramp. The uplift matches the formula every time. In the field, survey markers and GPS sensors track the rise and fall, confirming the predictions. The uplift isn't a mystery. It's the mechanical outcome of geometry, friction, and relentless motion. But the scale is staggering. Entire neighborhoods inching seaward, while the toe of the slide quietly builds new land, only to watch it vanish under the waves. This is the engine behind the rising seafloor off California, a process as old as the hills, now playing out in plain sight and measured in both inches and heartbreak. Satellite radar and deep borehole sensors have transformed the way scientists track the Portuguese Bend landslide, INSAR, or interferometric synthetic aperture radar. Uses satellite images taken days or weeks apart to detect shifts in the ground as small as a few millimeters, enough to spot a patio drifting or a road buckling before the human eye can catch it. The latest data reveal that some sectors of the slide are now moving at rates of 3 to 4.5 feet per month, far faster than the inch-per-year creep once considered normal. Below the surface, a recent drilling campaign reached depths of 300 to 350 feet, confirming a second, deeper slip plane beneath the well-known shallow layer. Geotechnical instruments in these boreholes record shifts in real time, capturing the cascade of movement that now drives the entire mass. According to one city engineer, the numbers are sobering. We're seeing rates and depths of movement that simply weren't on our radar before. These measurements leave no doubt. The scale of the landslide is larger, faster, and deeper than anyone imagined, with technology now providing the hard evidence that local residents have felt for years. The Portuguese Bend landslide now covers more than 700 acres, a hazard zone larger than many entire cities. Every new survey redraws the boundaries, pulling in homes, roads, and even parts of the coastline that once seemed safe. The numbers behind the response are staggering. Since late 2022, Rancho Palos Verdes has spent over $48 million just to keep up with emergency repairs and basic infrastructure. Another $18.6 million is already budgeted for the coming year, but the true cost continues to rise with every fresh crack and utility outage. In 2023, a federal FEMA grant brought $23.3 million in aid, but even that infusion only covers part of the most urgent work, mainly dewatering wells and road stabilization. The city's annual budget, less than $40 million, is stretched thin by the scale of the problem. Hazard maps now extend across neighborhoods that were never supposed to be at risk. City officials speak bluntly about the challenge. As the city manager put it during a recent council meeting, "We're fighting a war against geology that can only ever end in a draw. No amount of funding can buy permanent stability. At best, it buys time." The practical limit of mitigation is now clear. The slide is too vast, too deep, and too persistent for any single fix. For the people living here, that means learning to adapt to a landscape in constant motion, knowing that the ground will never truly hold still. In 2023 alone, sensors confirmed that parts of Rancho Palos Verdes moved up to 4.5 feet per month. an acceleration not seen since the 1956 reactivation. Decades of geological records show the Portuguese Bend landslide stretching over 700 acres, driven by ancient weak clay under the peninsula. While scientists now understand how downslope movement can push the seafloor upward, thanks to new drilling confirming a deep sliding plane, many questions remain. Experts still don't know exactly why the slide sped up so dramatically in recent years, or how to halt it. With $23.3 million in federal aid granted but costs far higher, city officials face tough choices as new land rises and is eroded away by the Pacific just as quickly. The evidence is clear. California's coastline is still being reshaped by forces that began millions of years ago. What happens next depends on both the science and the choices made today.